Okay, so we can start now. Good evening, everyone. I welcome you all to this week 5 live session of NPTEL course on deep learning. This course is offered by Professor Pravir Kumar Biswas, who is a professor in the Department of Electronics and Electrical Communication Engineering, IIT Kharagpur, and myself, Arka. I'm working as an NPTEL PMRFTA for this course this semester. So in this particular live session, we'll be following this particular roadmap. So first we'll solve the quiz of week 4, for which you guys already have been graded. And then we'll take up some problems, basically the practice problems for week 5. And as well as we'll try to see the Python coding regarding SVM KNN and how to deal with the data set for classification. Okay, so let's dive into the week 4 quiz. So the first question states that let X and Y be two features to discriminate between two classes. So we have two features X and Y, and there are two classes, class 1 and class 2. The values have been given in this particular table. The minimum number of neuron layers required to design the neural network classifier. So the uh, assumption is, if the problem is linearly separable, if the problem is linearly separable, as we have seen in the case of AND gate, OR gate, so using single neuron, we can get the classification done. So this is the main assumption. And if the problem is non-linearly separable, that means you cannot put a line to distinguish the classes. For those kind of cases, you need to go for multi-layer neural network concept or multi-layer perceptron. So given this particular assumption, let us first try to draw the uh, feature plane. So X and Y, and let's draw the grids. Okay. So over here, 1, 2. So that means this is 1, 2. Then 0, 0 is class 1 over here. Then you have -2, -2. Okay. Then you have -1, 1. And the last one is 3, 2. So 3, 2 over here. Okay. So now you can see that the problem is linearly separable. So you can just draw a line like this, or you can have n number of solutions. And if you use SVM, so then that will give you the optimal solution. For example, another classification boundary could be like this. So you have n number of solutions, out of which SVM will give you the optimal one. But the point is that this particular classification problem is linearly separable. Linearly separable classification problem. So if the problem is linearly separable, then we have seen the assumption is using just a single neuron, or a single layered network, then you can do the classification. So over here, the number of required neuron layers will be 1. Okay. So moving forward to the next question. Which of the among options give the range of logistic function? So what is the shape of a logistic function? Anyone?
Sigmoid.
Sigmoid. So sigmoid is basically ranges from, it looks like this. So it could be more smooth. Yeah. So this is 1 and this is 0, and at x equal to 0, let us consider this is x and this is sigma of x. So at x equal to 0, you will get 0.5. So this is how sigmoid looks like. So what is the range of the sigmoid function? So it ranges from 0 to 1. So that means sigma x basically ranges from 0 to 1. So this is the final answer for this particular question. Then the next question is input to softmax activation. So let us consider you have a vector v, which is 5, 3, and 4. Now what you do is you apply a softmax function. So softmax function you apply over here, and you need to get the output O. So O will be O1, O2, and O3. So you need to evaluate what is the value of O1, O2, and O3. So what is the equation for softmax function? Anyone?
E to the power vi divided by summation of e to the power vi.
Yeah. So summation of e to the power vi for all I. Okay. So by that same logic, your O1 will be e to the power 5 divided by e to the power 5 plus e to the power 3 plus e to the power 4. O2 will be e power 3, e power 5, power 3, e power 4. I think someone's mic is on. Please turn it off. And O3 would be e power 4 divided by e power 5, e power 3, e plus e power 4. So obviously you can use your calculator in mobile or scientific calculator. You can use it to solve the to get the values of these particular functions. However, as far as the examination is concerned, in the examination hall, you might not be allowed with scientific calculator. So they will provide you the on-screen calculator, and that is basically what is used in GATE exam. So I request you all to start practicing the solution of these kind of questions using the GATE online calculator. So you will get a command over there. Otherwise, what will happen in the forum itself? I saw someone has written to verify the answers. So probably he had some issue while using the calculator, and probably he got the wrong answer for that. So uh, you should start using that particular calculator. It will help you in the final exam. Otherwise, you will be stuck with these calculations if you don't know how to use that particular calculator. It's so if you just solve it over here, the values that we'll get is 0.665. O2 will be 0.090 and O3 will be 0.244. So over here, you can see that option D is the nearest solution. So you can just write it at 0.67. You can approximate it. So option D is the correct answer. Then the next question states that which of the following yes.
Is there any official link to Gate Calculator?
This just search it in the web. So whatever, for example, Even I think in Chrome, this particular calculator you can use. Okay, so this is provided by TCS IAM.
Yeah.
Otherwise, you can use Google Chrome. There are several extensions are also there, so you can just plug it into your Chrome. So you can get any sort of Google Chrome extension. So you can use that one also. But specifically, I would recommend to use this one.
Okay, thank you, sir.
Okay, so the next question is which of the following option is true? So in batch gradient descent, so a batch gradient descent basically means a full batch gradient descent. So there are three versions of gradient descent. So one is stochastic gradient descent, which basically considers one sample at a time. One is batch gradient descent, which considers the whole dataset as a whole and then calculate the loss and then do the backpropagation. And another one is mini batch gradient descent, which basically considers a small subset of the whole batch. It feeds that small subset into the network, calculates the loss, accumulates it, and then do the weight updation using gradient descent. So over here, let us start scanning the options. So in the first option, it is written that in batch gradient descent, a small batch of samples. So in batch gradient descent, there is no concept of small batch. So this refers to mini batch gradient descent. So this particular option is incorrect. In batch gradient descent, whole data set is processed together to update the iteration in each iteration. So it is okay. Batch gradient descent considers only one sample. So again, it is wrong because one sample is basically corresponds to stochastic gradient descent. And batch gradient descent produces noisier update than stochastic gradient descent. So this is also wrong because in stochastic gradient descent, what you are doing, you are basically calculating loss and updating the weight values for each and every sample. So for each sample, you will get something like this. So this will be more noisier because you are considering loss for each and every sample. However, in case of batch gradient descent, you will get smoother than stochastic gradient descent. Okay, so by that logic, option B is the correct one. Option B is the final answer. Okay, moving to the next question. So you need to choose the correct options out of these four. So inability of a model to obtain sufficiently low training error is termed as overfitting. So let me first define what is overfitting and underfitting, and then we'll scan through this particular solutions. So let us consider you are training a model. So let us consider this is iteration, and in the y-axis you have, let's say, loss. So let's say your blue curve basically refers to training. Blue is for training and red is for testing. Okay, so from this particular curve, you can see that while training the model, you are achieving very good loss value. That means almost it is equal to zero, almost it reaches to zero. However, while testing the same model after training it, so you can see there is a substantial gap in between the training loss and the testing loss. That means while training the model performs very well. It is able to recognize each and every sample from the training data set. And while testing the model, your model is not able to perform that well, which was there in the case of training time. So this particular gap basically shows that the model is overfitted. Overfitted means while training the model, it performs very well, but while testing the model, the model performs significantly, it gives significantly poor result. So this phenomena is called overfitting of a model. And let us consider another case. For example, you have two data sets like this. And another one is this. So in some cases, what happens is that your model, while training, so this is your training data set, training data set. So while training the model, let us consider the ideal decision boundary will be something like this. Ideal decision boundary, something like this, so that you can get very good classification accuracy. But let us consider due to some mishap or some uh, irregularity while training, it is not able to capture that what could be the possible decision boundary. It is the decision boundary predicted by the model is something like this. So that means from the training data, from, let me change the color. That means from the training data, model is not able to capture any significant information to classify the data, or in other words, or the model is not able to classify well in training phase itself. In training phase itself, that means while training itself, your model is performing very poor. So if I show you the loss curve again, so this is the loss and this is iteration in x-axis, iteration. So your training curve itself is something like this. That means you are incurring huge amount of loss while training. So that means this condition refers that your model is not able to classify well in the training phase itself. So this problem, so high training error refers to uh, underfit. Underfit means that the model is not able to understand anything from the training data itself. Therefore, the training error is very high, so as the testing error will also be very high. That means the model is not able to capture any relevant information. So let us now scan through the options. So first option is inability of a model to obtain sufficiently low training error is termed as overfitting. So this is wrong because we have seen that inability of a model to obtain sufficiently low training error. So that means they are referring to this particular case. So that is not at all overfitting. Then inability of a model to reduce large margin between training and testing error is termed as overfitting. So we can observe that the model is not able to reduce the margin between testing error and training error, and there is a substantially large gap between the error values in training and testing. So this is called overfitting. So this particular option is correct. Okay. Inability of a model to obtain sufficiently low training error is termed as underfitting. So this is correct that if the model is not able to reach sufficiently low training error, so then that means the model is getting a high training error in the training phase. So this process is underfitting. So that is what we have shown over here in this particular graph. The model is achieving very high training error, and it is stating that inability of a model to obtain sufficiently low training error. So that means the model is not able to achieve sufficiently low training error. That means it is achieving very high training error. So this process is called underfitting. So as per the diagram also, we can observe that this is basically what is referred by underfitting. And the last option is inability of a model to reduce large margin between training and testing error is called underfitting. So again, this is wrong because that is what is meant by overfitting. So option 2 and option 3. So option B is the correct option because both option 2 and 3 are the correct one. Okay. So any confusion on this particular question?
Clear, sir.
Okay, so let me proceed with the next one. Okay, so again, you need to choose the correct options. So choose the correct option about given these particular assumptions in machine learning. So data samples in each data set are dependent on each other. So on the first, from the very beginning of the live sessions, I showed you one such example is that let us consider this is a vector from class A, and this is a vector from class B. So these two vectors are dependent as because I can write B is lambda into A, isn't it? That A is larger than B, but they are collinear. So that means there will be a scaling factor. Let's say B is let's say A is twice of B. So you can write that 2 into sorry A is lambda into B. So in our case, let us consider lambda is 2. So this is twice of B. So we can observe that the vectors are collinear, and as because I can write A in terms of B, that means they are dependent also, dependent. So now let us consider you are training a model by feeding these two data, Now let us consider this is a model M, and you are feeding these two particular data to get it classified into class A or class B. As the data itself is dependent on each other, so your model will not be able to distinguish that which of the data belongs to which particular class. So there is no distinction. However, if the case was like this, so let us consider your B vector is like this and your A vector is like this. A, and let's say this is B. Let us consider the angle between these two are perpendicular, a 90-degree. That means orthogonal to each other. So if I take A dot B, so it would be mod A mod B cos 90. That means 0. So whenever the dot product between two vectors are 0, that means they are orthogonal and they are independent of each other. Independent of each other. So if you feed these two data into the machine learning or deep learning model, so as you can see that A and B has no dependency. Therefore, your model will be very happy to classify these particular data. However, in this particular case, in the first case, you can see as because there is a dependency, your model will get a hard time to classify or to distinguish which of the data belongs to class A or class B as because they look alike. However, in this case, you can see that A's direction is totally different than B. So that means they have no dependency with each other. and which is why your model will get very it will be very easy for the model to get it classified into whether the data belongs to class A or data belongs to class B. So machine learning, deep learning, nobody basically likes to get any dependent set of data. So always we talk about the independence and the orthogonality of the vectors. In the subsequent lectures also you will see PC and all. So where you will see that the what is the role of orthogonality in detail. So from this particular inference, so we can from this particular analogy we can infer that this statement is wrong. The data sample in each data set are dependent on each other. So we don't want this particular scenario to happen in case of machine learning. Each data sample present in training and test set are independent of each other. Then let us scan through other solutions also. Training set and test set are overlapping to each other. So let us consider, let us elaborate this particular scenario. So let us consider your training data is like this. This is your training sample. Let us consider from class A. You have two class A and class B. So what they are saying, they are overlapping. So overlapping means like this. Overlapping. So this is the situation. So this red basically gives you the testing data and blue dot gives you the training data. Now, if these two data sets are overlapping to each other, so that means it is very likely to have the same training and testing data. So what is the novelty in classifying the training and testing data set if they are belonging to same particular data? So that means if they are overlapping with each other, so that means they are coming from the same data distribution. And if the same thing happens, then you can see that whatever data is there in case of training data set, you are getting the same data from you are getting the same thing at the testing data. So in training, while training the model, you are able to classify it. And now the same data comes from at the testing data, and again you are getting it classified accurately. But there is no novelty in this particular case. So this assumption is also wrong. So the next assumption is the distribution of training set and test set assumed to be identical. So for this, if I show you one such example, uh, just so if I show you the images, then it will be very easy to infer from the analogy itself. Yes. So here you can see that let us consider you have truck class. So over here you can see an image of truck. Over here also this is an image of truck. So overlapping case means let's say you will see the same type of image. For example, you will get some other version. For example, this image is flipped by 90 degree or flipped by 180 degree, and the object remains the same. So that means you will get different copies of this particular track only. So that is what the overlapping means. But now you can see these two are track. Obviously, these two are tracks, but the images look different. What it basically means is that, let's say this is a probability distribution of a track. So if you sample the data from this point or from this point, you will get two different looking tracks. So their look will be different, but they are sampled from same distribution, which is the case over here. So these two are tracks. If you take histogram of these two cases, so you will see that there is similarity in between the probability distributions. So that means for a machine learning data set, they should not be overlapping with each other. That means, for example, if you have A, or you are getting another version of this particular image itself. Let's say it is just flipped about this particular axis. So it is just flip of this particular image. So we do not expect something like this. However, what we expect is their probability distribution could be identical, and if you sample from the probability distribution, you will get different set of images that belongs to the same class. So over here, the distribution of training set and test set are assumed to be identical. So from this particular image, you can observe that if you just rotate this particular image, you will get another copy of the same image. But we do not expect that. We expect like something like this. So the images look different, but if you take histogram of these two particular images, you will see that there is similarity in the distribution. So, and in the last coding session, I show you that how to plot a histogram. So you can just use the previous classes code, and you can by yourself you can evaluate the histogram. So you will see that there is some sort of similarity. For example, over here also frog. So you can see that these two frogs looks totally different. If had it been the case that they are overlapping, the data are overlapping, so you will get a different copy of this particular image, let's say horizontal flip or vertical flip or some angle of rotation is there. But the main point of concern is their data distribution should be kind of identical, which basically generates different sort of data. So that means one frog will look like this, another frog may look like this. So for example, over here also you can see another frog. So they look quite a different, but if you plot the histograms, then you will see that the probability distribution might look alike. There should be some similarity. So by that logic, option 4 is one of the correct answer. Then you have so option 3 is also incorrect. Each data samples present in training and test set are independent of each other. So that is what we talked about. Like we do not want something which is dependent with each other. So in machine learning, we need some sort of independence. So therefore, the option 2 is correct one. So the correct option will be both options, option 2 and option 4. So any confusion for this particular question?
Clear, sir.
Okay. Okay, so the next question states that you have an artificial neural network which receives n inputs. So that means if I just draw the diagram, so these are the neurons. So x1, x2, x3, and you have n such input values. So this is x of n, and with the corresponding weights, W1, W3, Wn and all linked to the inputs and the weighted sum. So you have a neuron over here which is connected like this. So there will be n such connections and the weights are given W1, W2, W3 and W1. Sorry. So you need to get the weighted sum. So you need to get the value of y. So what will be the value of y? It is simply just the linear combination W1 x1 plus W2 x2 dot 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 Wn xn. So I can just generalize this particular thing. So for all I, Wi xi, or you can write it as I equals to 1 to, let's say, n number of such samples. So Wi xi. So option D is the correct one. And what it basically says is that the weighted sum I Wi xi is computed to pass on to a nonlinear filter. That means this is where you get y and then you have a nonlinear filter. Let us consider this nonlinear filter could be ReLU function. It could be sigmoid. It could be threshold also. And then what you get is sigma of y, or you can write it as sigma of summation Wi xi. So this is what is the heart of any neural network. So you get a weighted sum, then you apply a nonlinear filter to get this sort of equation. And this is the output of the final operation. Okay. So the next question states that let us assume that we implement a AND function using single neuron. And it will be implemented using single neuron because we have seen in the class itself that and in case of and you can from the truth table itself you can see that the problem is a linearly separable problem, and any linearly separable problem can be solved using a single neuron itself. So the activation function f of NL is of a neuron is denoted as, so they have given definition of the nonlinear function and what would be the possible combination of weights and biases. So they have given some weights and biases, and you need to see that for which of the weights and bias values you are getting correct classification of the and function. So how many of you got this particular question correct in the quiz? Okay, so what would be the approach? How did you solve this quiz? Anyone? This particular question?
Actually, I have taken here the activation function, that is y less than 30, which has been rounded to 1. And greater than, greater than 30 is rounded to 1 and less than 30 is 0. And I have applied all the possible combinations for this given for an AND gate solution. That is what I did.
Okay, so did you use a truth table or?
Yes, that truth
Yeah.
table combination.
Yes.
I think only one combination, that AND gate truth table, was working fine. The remaining choices were not coming out correct.
Yes. So that is the key for this particular solution, that you need to use the truth table, and from the truth table, you will get to know that which of the answer is actually correct. So let me.
One
Yes.
query.
Yes.
Any other way? Because after all, for exams, time matters. So here I have tried out all the 4 possible outputs given
Yes,
choices,
yes.
and then I found out. Is there any other way of doing it?
the only catch is that in the question, if they give you any, for example, you have 4 such so if they provide the values of x1 and x2, if they provide the value of x1 and x2, then it would be more easier
Easy.
to understand.
Yeah.
Yes. And if they do not provide the value of x1 and x2, then you have to consider all 4 cases, because you need to match that for which of the cases the options are not working. So you have to do the whole thing. So there is no other alternative. So you need to do the whole calculation. Anyway, I think with practice it will be more easier, because otherwise
Okay.
it will
One more query, sir. There was
yes.
one more question with I think with OR gate, with OR function.
Yes, yes.
So there I had actually answers which was having almost a similar match. So there, how to find out which is the correct option?
Okay, so I will solve the OR gate problem also. So let us first do this one, and then I have stacked that particular question. I think this one you are.
Yes, sir. Yes.
So we'll solve this one also. So for an AND gate over here, so you have so this is a 2-input AND gate, and we know the possible class. So let us consider this particular class observation is P, and over here your neural network output is P hat. So the 0 0, the truth, let me write the truth table 0 0 0 1 1 0 1 1, and 0 0 0 1. So you need to scan through all these possible combinations. So let me start with option A. So option A, they have given, so, and let me just write the equation also. So y will be w1 x1 plus w2 x2 plus 1 into bias. Let me abbreviate the bias as b. So b into 1, so I can directly write it as b. And P hat is FNL Okay, so the definition of the nonlinear function is given as if NL of y will be equal to 0 if y is less than 30, and it is 1 when y is greater equal to 30. Okay. So you need to follow this particular nonlinear operation. Now let us scan through option A, where they have given W1 is equals to 5, W2 is equals to 25, and bias value is equal to 5. So what will be the value of y for 0 0 case when x1 and x2 is equal to 0? So the equation is this one. If x1 and x2 is 0, then the multiplication will be 0 0. So 0 plus bias value is given as 5. So y is equals to 5. Now you apply FNL. So you have seen that from the definition, if y is less than 30, then output is 0. So you can see that output is 0 if you apply the nonlinear function. And it matches with the class identity also. So if the input is 0 0, then output should be 0. So that is what you are getting over here. So if the input x1 and x2 is 0 0, then your output is 0. So it is matching. So the first case is okay. So let us go for the second case 0 1. So y will be 0 plus 1 into W2, so W2 is 25, so 1 into 25, and then B, so over here it is 5, so total is how much? 30. So if you apply now if you apply FNL, so you can see that when y is equal to 30, then output is how much? 1. But you can see from the truth table itself, if the inputs are 0, 1, output should be 0. But what you are getting is 1. So that means this is incorrect. So the moment you are getting incorrect option, don't go for the next case. The next case, I mean the 1, 0 and 1, 1 case. So option A is incorrect. Let us move to option B. So in case of option B, the values are W1 is 5, W2 is 5, and sorry, this bias is 10. So again, let us start with 0, 0 case. So it will be 0 plus bias, which is 10. And if you apply the nonlinear function, obviously you will get 0 because the summation is yield to 10. Now the second case where 0, 1 exists, so it will be 0, then 1 into 5, it will be 5, and then 10. So total is how much? 15. Now you apply the nonlinear function, again you will get 0. So that means again the condition satisfies. So let us proceed for the next one. So in the next one, you can see that x1 is 1. So over here you will get 5 plus 0 plus 10. So again it is 15. And if you apply this particular solution, so you will get 0. So the third condition is also satisfied. So let us see for the last condition. So let us check for the last condition, that is 1, 1. So for 1, 1, you will get 5 plus 5. 5 plus 5 plus 10. So it is how much? 20. So now if you apply f of the nonlinear function, so you can see that your summation is 20, which is less than 30. That means your output will be 0. But you can observe that for 1, 1 case, your output should be 1, but you are getting an incorrect output over here. So that means you can nullify this option as well. So option B is also incorrect. Fine. Now you go for the third option. So in case of third option, you can write that the values are given as W1 is equals to 15, W2 is equals to 15, and bias is equals to 10. So at 0, 0 condition, so if I just copy these things, let me copy this part as well. So this is the equation that you have to follow. So for the first case, that means 0, 0 case, our y will be 0 plus 0 plus 10. Now you apply nonlinear function, you will get 0, which is fine. Then second case, for 0, 1, it will be 0 plus. Yeah, Anurag, your mic is on. So it will be 0. Then for weight 2, it will be 5, and then bias. So again 15. F of the nonlinear function will give you 0. Then for the third case, that means 1, 0 condition, you will get 15 plus 0 plus 10, which is 25. And again, if you apply nonlinear function, then you will get 0 over here. And for the last condition, let us check. So it will be 15 plus 15 Okay, so both are 15, right? So over here it will be 25. So 15 plus 15 plus 10. So it will give you 40. So now you can see that if you apply f of the nonlinear function due to this particular definition that we have written over here. So let me copy this part as well. So now you can see that f of NL is equal to 1 whenever y is greater than equal to 30. So over here you are getting 40. So your output will be 1. So you can see it is matching 0001 and over here also it is 0001. So that means option C is the correct option. So you don't have to go for option D as well because you have seen that for option C all the conditions are satisfying. So in exam, if they do not provide that what is the value of x1 and x2, you have to go for the whole calculation. Okay, so any confusion for this particular question?
Sir, in lecture, it is solved using the matrix. Okay, so first it is taken bias, then the W1, W2. So why we have to take, sir, first bias only? Why not W1, W2 first, then bias?
You can use W1, W2 before. For example, you can write it like this also. There is no problem with that. So why he has written? Because he constructed the weights like that particular way. For example, in his lecture, in professor's lecture, you will see that one is kept at the top and then x1 and x2. It is just for the representation, how you want, how you actually want to represent it. If you start with x1 and x2 first, then you have to put the you have to put this particular sort of representation for the weight. However, if you put one at the top, then your weight representation will be B, then W1, then W2. Now, as far as the summation is concerned, so you can see for both these cases, if I write the equation of y for both these cases, this will be y will be W1x1, W2x2 plus B, as because it is weight transpose into X. So your weight is, if I take transpose W1, W2, B, and your X is X1, X2, 1. So if you do the multiplication, it will be what? W1, X1 plus W2, X2 plus B. Now, the moment you represent it like this, your representation for X also will change. So it will, the representation of X will be 1, x1, x2, and W's representation will be B, W1, W2. So if you do the W transpose X, you will get B, W1, W2, and 1, x1, x2. So again, you will get the, you will end up on same equation. Okay, so that means there is no issue with these representations. You can use either of these two representation. Either you put x1, x2 at top, bias at the bottom position. Otherwise, you can put bias term on the top and put the features on the bottom position. So any of the representation is correct.
Sir,
Yes.
but in 10th question, if we put reverse order, na, answer is not getting the answer.
So
This
for
question
this,
only, sir. Bias,
so
if you
what order?
substitute
What
the
order
bias
you
value
have
is
put?
first. Bias x1 and x2, W1, W2, like that.
So whatever order you put, for example, for this particular option, so you are asking that you put bias at the top and x1 and x2 at bottom, right? This is what you are saying.
Yes, sir.
So for this, for this particular case, if I just, you need to rearrange all the things. For example, for x1, the associated weight will be W1. For x2, the associated weight will be W2. And for bias term, the weight will be B. Now, if you do the output Y, it will be W transpose X. Now, your W looks like B W1 W2, and your X will look like B. Sorry, your X will look like 1, 1, X1 and X2. Okay, so with this particular convention, let me solve. So let me omit this particular image. So I will not consider this particular image. I will solve the question with this configuration, and let me check whether the answer is correct or not. So
Sir, based on this method, answer is coming correct. But B, if you put down W1, W2, B, that we
that
cannot
means
get
this
the answer
particular
proper.
condition. That means this particular condition.
Yes, yes, sir.
It will come
The
same.
bias
So
value.
it will come same. Let me show you then. So you have
Okay,
used.
sir. Okay.
Okay. So over here, let me.
Sir,
Yes. Please go ahead.
matrix format. I use
Yeah,
matrix format.
format.
In
Okay.
equation
No.
format, we will get the answer properly.
Okay.
In
Let
matrix
me
format. Okay.
let me use matrix format only then.
Okay.
The matrix
Okay,
format for the input will be x1, x2, and 1, and the matrix format for the W will be W1, W2, and let me write bias as B. Okay. So the Y is W transpose into X, right? Now the W, if I take W transpose, it will be W1, W2, B, and the X is X1, X2, and 1. So this is 1. So now if you take the dot product between these two, it will be simply W1 X1 plus W2 X2 plus B, right? So from directly you can see that W1 will be multiplied with X1, W2 will be multiplied with X2, and 1 will be multiplied with bias. So by whatever method you use, whether it is matrix multiplication or just doing this linear combination, direct linear combination, you will end up on same equation. And if you end up on same equation, obviously you have to get the obviously you will get the same answer.
Yes, sir. That I understood, sir. But in professor lecture notes, W transpose, sir has told us 100, 101 like that. That matrix format.
I think he has taken some. So the representation will be something else, because I have shown you two such cases that either you consider the inputs like this or you consider the inputs like this. So whatever approach you use for matrix multiplication, it will end up on same equation. So for this also you are getting y equal to w1 x1 plus w2 x2 plus b. For this representation also you will get b plus w1 x1 plus w2 x2. So eventually they are same. So I think probably there is some issue at your side while doing the calculation. Otherwise, what you can do, you post the query with the notation. In the forum, I will check and I will do the solution accordingly, because I'm not able to understand that at what point you are getting stuck with the matrix multiplication or with the representation.
Okay, sir. I will post it.
Yes.
Yeah. Okay. Thank you, sir.
Okay. Because basically you should end up on the same equation. Whatever approach you use, your linear combination equation, you should end up on the same equation, whatever approach you use.
Sir
Okay.
has included that combination also, the input combinations also as vectors, like
So is it
101. So that combination is also included inside the matrix. The input combinations, x1, x2 combinations.
okay? Yeah, that is what we are doing also. For example, if I write the OR gate x1, x2, and y 0, 0, 0, 1, 1, 0, 1, 1. So let's start with option A. So in case of, let me use this matrix operation itself. So in case of option A, you've been given that W1 is equals to 1, W2 is equals to 1.5, and B is equals to 1. So you start with 0, 0 condition. So your x will be 0, 0, 1, and your W is 1, 1.5, and bias is 1, right? So you do the matrix multiplication, it will be 0 plus 0 plus 1. So it is 1. So is there any difficulty for this particular case? Or for example, here also I am including x1 and x2 and the bias term. So are you guys referring to this sort of? So I'm not able to understand the anomaly where you are getting stuck over here.
This understanding, sir.
Uh,
Uh,
so this matrix multiplication is okay, I think. So is there any issue with this particular matrix multiplication? And how I'm... Yes, please go ahead.
Sir, whole matrix. You put whole matrix and explain, sir. Single term
Okay.
you're using now, sir, for all these three values in same one matrix form.
Yes, but you cannot feed this whole matrix into the neural network. Your neural network accept x1, x2, and 1. And x1 is of shape R1 cross 1, x2 is of shape R1 cross 1, and 1 is, that means they accept the scalar value. You cannot feed this whole matrix at the same time. What I mean is that this is class. This is class, whether the data belongs to class 0 or class 1, and this is your input vectors. Now the input vectors that you have, for example, consider it as a batch. In a batch, you have 4 samples. So this is sample 1, this is sample 2, sample 3, sample 4. Now let us consider a full batch gradient descent case. So you will feed this thing first, then you take the output, calculate loss. Again, feed this one, get the output, calculate the loss. Feed this one, get the output, calculate the loss. So that means you are feeding one by one. You cannot feed this whole thing at a once.
Okay, sir, I understood, sir, but I tried like Professor Lecture 19th video. Based on that video, and logics are solved with whole matrix. Like
with
that,
whole matrix.
Yeah, like that only I tried, but I got the answer correctly. But bias have I want to put in upper. B.
Okay.
After that only W1, W2.
Okay.
So I asked
So
the
so
doubts.
so can you share? Can you so what you do? Because I also have to see that how he has solved.
Okay, sir.
So what you do? You share. I think for this particular week already marks are send out to your account or the
Nice.
login ID. So I think now you can share your solution in the forum. So if I see the solution, then I will understand that what you have done or
Okay, sir.
what approach you have incorporated.
Okay, sir.
So
I will upload my.
yes, I will see it, and then if any anomaly is there, so I can reply on that on the next class, obviously, or in
Okay, sir.
the chat itself.
Yeah, okay, sir. Thank you, sir.
Okay. So over here you can see that for the first option, your output is y is equals to 0 plus 0 plus 1, which is equal to 1. And if you apply the nonlinear function, it will be 1. But for 0 0, you can see that your output should be 0, but you are getting over here 1. So just omit this particular option A. Option A is incorrect. Then let's go to option B. So over there, in case of option B, your y, let us start for 0, 0. So you will get 0 plus 0 plus your bias is -1. So over here, your bias is 0 plus 0 plus -1. So -1. So you apply the nonlinear function, you will get 0. Fine. Y is equals to 0. Then W2 is 0.5 and then -1 again minus 0.5. So if 0 is 0, so you should get 1, but you are getting 0 over here. So again, this is incorrect. Then option B is also omitted. Let us go to option C. So option C. So the first one will be 0 plus 0 plus bias is -1. So if you apply the nonlinear function, we'll get 0. So this is the first thing is correct. Then let us search for the other cases. So the case 2 is, let me just copy this particular thing. So this is again option C we are looking. So case 2 is 0 plus the weight 2, that is 1.5 minus 1. So you are getting 0.5 over here. So 0.5 is greater than 0, so you will get 1. Okay. Then you have the next case 1 plus 0 and then -1. So you are getting 0. And if you apply the nonlinear function, you can see that if it is equals to 0, then also the output is 1. So this is 1. And at the last condition, the value of y will be 1 plus 1.5 minus 1. So this is 1.5 over here. And if you apply f of the basically the nonlinear function, then you will see that output will be 1. So you can see that for all the conditions. So in the previous page, the first condition was written. So you can see for all the cases, it is satisfying the class information. So 0, 1, 1, 1. So it is giving you 0, 1, 1, 1 pattern. So that means option C is correct one. So rest of the options are incorrect. So any confusion on this particular question?
No,
No,
sir.
sir.
Okay. One second. Okay, so we can start taking some week 5 practice questions. So the question is, can you identify that what are these nonlinear activation functions? So this nonlinear activation function, you can see that it ranges from 0 to 1. So what here the value is 0.5. So what is this particular nonlinear function?
Sigmoid function.
Yes, so this is sigmoid. Then over here, the value ranges from +1 to -1. So what is this one?
Leaky.
No. So this is actually tan h.
Yes, sir.
Hyperbolic tangent function ranges from -1 to +1. So this is tan h activation function. So what is this particular
Second
activation
one,
function?
Really.
This is
Relu.
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 Yes. So in case of ReLU, you can see that the function is max of 0, x. So whenever x goes in the negative direction, the output will be 0. That means for the positive direction, you can see that the value will be x only, and for the negative side, the value will be clipped to 0. So to avoid, so this is what is basically meant by ReLU. But in case of what you call the this particular scenario, you can see that there is for the positive half, the answer is x. Matlab the response is x. And in the negative half, you can see that there is no clipping to 0. So this angle is called alpha, and this activation function is called leaky ReLU. Why it is leaky? Because in the negative half, you can see that the data is not clipped, it is leaked to some particular alpha angle, and depending on the negativity of the x, the value will be decided based on this particular alpha. So given this, so this particular nonlinear function is called a leaky ReLU activation function. That means for negative half side, there will be no clipping to 0. It will also have some finite value. So this is what leaky ReLU is called. So I think in class you've been told that what is sigmoid function, what is tan h function, and how ReLU function looks like. And over here, this is the representation of a leaky ReLU function. So you can search, there are several more activation functions like swish, then different versions of ReLU. So ReLU actually was invented first, and then people started exploring different versions of ReLU. So leaky ReLU is one such of version of ReLU. Then you have GeLU, then you have SeLU, then you have ALU. So there are different versions of ReLU is also available. Then Swish, then you have soft and hard Swish. So there are different variety of nonlinear activation functions are available, and in each of them you will see that slight variation is there. For example, in case of GeLU, the functions looks like this. So it is having some sort of constant value in the negative half side, and in the positive half side, it is having same response as x. But over here, you can see that there is a sharp transition, that the value is at origin is 0. Over here also the value at origin is 0. So they introduced, there is a some dip, and then it can go to x. So this is a venture of research also, that what should be the graphical representation of each of these activation functions. So people actually introduce different sort of activation functions nowadays. So if you can see the recent literatures, you will see different varieties of activation function. And if you are started the Python coding by yourself and constructing the neural network, then you will see in the Keras web page that whatever activation functions are available, you can plug and play with them.
Sir, in case of a leaky ReLU, that it will be always there in the third quadrant only, that leaky part.
Yes, it will always be there in the third quadrant. So the equation has been constructed in such a way. So there is another version, for example, in probably last to last year, there is a very big conference, CVPR is there. So so two Indians were there. So they proposed different version of sigmoid. It looks like this. So it reaches to 1 and 0 when you increase the value, but there is a glitch over here at both the lobes. In the upper side and in the lower side, there is a glitch. So they propose that why we should consider the glitch and all. So this is again what I was telling, that people are introducing different sort of activation functions nowadays. So they have their merits and demerits as well. But these are sort of textbook things, because these are quite old. So people use this, but nowadays you can see several new combination of activation functions are also coming. For example, several people have merged the activation functions. For example, sigmoid plus ReLU, like that. Then leaky ReLU, and there is some combination of tanh, and then they get some other function, and then they use it as activation function. So they rename it something like that. So this is how the current research is going on in the field of activation function itself.
That means, sir, in leaky ReLU, the first quadrant always it will be constant only. It
Not
cannot be
not constant. You can see that it follows the trend of x. That means over here the equation is y equal to x. For example, if the value is x equal to 2, y will be also equal to 2. So for example, over here the equation is what? The equation is y equals to 0 for this half. And over here the equation is y equal to x. If I write it like this, y equal to max 0 comma x. So there will be two conditions. If x is less than 0, y will be what? Y will be equal to 0. And if x is greater than 0, then max of 0 comma x will be x only. So y will be equal to x. So over here also you can see that this is y is equals to x only. And over here you will see that y is equals to minus of alpha into x. Oh, sorry. So this is alpha into x. X is already negative. So that means it is giving you negative value. So if you put, for example, x is minus 10, x is minus 10. So you will get alpha multiplied with 10. So if alpha is, let's say, 0.3, generally alpha is ranges from 0 to 1. So if alpha is equals to 0, then it will convert to normal ReLU, because alpha equal to 0 means y is alpha into x. If you put alpha equal to 0, y will be always 0. But if you put so it will be only parenthesis. And if you put anything in between 0 to 1, so let us consider, let me take alpha equal to 0.3. So it will be alpha into x. So 0.3, and let us consider you are going to negative side. So let us consider x is equals to minus 10. So the value will be y will be equal to minus 3. So you will get value in the third quadrant itself.
Okay, sir. Thank you.
Okay, so the next question is quite similar like what you have seen in week 4 quiz. What is the output of sigmoid function for an input with dynamic range 0 to infinity? So what will be the range from 0 to infinity of a sigmoid function?
0.5 to 1.
0.5 to 1.
Yeah, 0.5 to 1 because the sigmoid function looks like, so this is 1. So you've been asked to move from 0 to infinity. At 0, the value is 0.5. At infinity, the value will be 1. So therefore, the range will be 0.5 to 1. Okay. Now here comes the gradient descent related problem. So you've been given a neural network architecture like this, which has 2 input, 1 bias, and you have an output p hat. So what will be the equation of p hat?
X1 W1
X1 W1
plus X2 W2 1
plus 1
into
into B.
W naught B.
Yeah, so X1 W1, X2 W2 plus B. Okay, and you have a loss function J, and J is denoted as half P hat minus P whole square. Okay, so where P is the target and P hat is basically the output of the neural network. Now, the question states that you need to calculate del J divided by del W1. So you can see that P hat is a function of W1. Is it not? P hat is basically function of W1, W2 and bias. So obviously, if I write it like this for the sake of completeness, P hat is a function of W1, W2 and bias. And you've been asked to find the gradient with respect to W1. So what will be the chain rule for this thing? Anyone?
Yes, sir. So 2 times of p hat minus p.
No, no,
And,
no. First, tell me the chain rule for this. If I have to evaluate del J by del W1, then how should I proceed with the chain rule? And then I obviously will go to the final answer.
Del J by P
P hat actually, because
hat.
P is target, your output is P hat. So P hat, then
And then del P hat by del X1.
no, you have to calculate, you have to take gradient with respect to W1. So it will be, yeah, del W1. So this is the chain rule for this particular case. So let us start evaluating. So this will be half into 2 into P hat minus P for the first one. And for the second one, it will be with respect to W1. So it will give you X1 and rest of the things are constant for this. So it will be 0. So x1 into p hat minus p, right? So option C is the correct option. So similar kind of question you'll see in the week's quiz for week 5 quiz. So you've been given some sort of neural network architecture and then you have to calculate the values for the gradient. Let us consider you can actually you can be asked like you need to find del J by del W2 or some other configuration is also given. Let's say X3 is given with W3 and then you need to find del J by del W3 like that. So n number of problems can be imposed from the same set of representation. Okay, so any query for this one?
Sir, please explain how the derivative has been done.
Okay, so uh, so let me pick another page. So p hat, you have got that how to extract p hat. This is just simple linear combination. You multiply x1 w1, x2 w2, and 1 with bias. So you got p hat. Now in the question, you've been given j is half e hat minus p whole square. Now you've been told del j by del w1. So now you can see del j is a function of p hat, right? J is a function of p hat.
Yes, sir.
Yes, but you cannot directly see that how you cannot directly see any w1 in this particular equation, right?
Yes.
You can see only p. So let us now check whether p hat is dependent on w1 or not. So this is the equation of p hat, right? And now you can see that p hat is a function of w1, because you can see there is a multiplication w1 into x1. That means p hat is dependent on w1. So to take the gradient, first what you have to do, first you have to take the gradient with respect to p hat, because j is dependent on which of the function p hat, and then you can see that p hat is dependent on w1. So you take the derivative with respect to w1 of the p hat. So now from the chain rule, you can observe that this del p will cancel. So you will end up with del j by del w1. As because you cannot see any term of w1, so you need to use the chain rule. First, j is dependent on p hat. So you need to take the derivative of j with respect to p hat. And then you scan that p hat depends on w1. So you take derivative of p hat with respect to w1. And this will give you del j by del w1.
Yes, sir. Thank you.
Okay. Yeah. So in the next question, it is stating that which of the following options are the potential benefits of using ReLU activation over sigmoid activation? So before going to the solution, let me just draw the activation functions, and then it will be helpful to illustrate the question. So this is ReLU. So for negative of x, it will be clipped to 0, and for positive of x, it will be like this, y equal to x. And over here, in case of sigmoid function, it will look like this. Okay, so 0 to 1. ReLU of x, and this is sigmoid of x. So in case of uh, gradient descent, in the lectures, you have seen that while doing the evaluating the gradient, one term basically comes. Let us consider you have a function sigma of w1 x1. So let us, this is f, and what you have to do is you need to take the derivative with respect to w1. So can anyone actually tell me that what will be the derivative? What will be the final answer for this particular derivative?
Sigmoid into 1 minus sigmoid.
Yeah, sigmoid into 1 minus sigmoid. That means uh, That means you have to write it like this. For example, if you write P is equals to sigma of X. If you write P is equals to sigma into X, and then you take the derivative, it will be sigma of X 1 minus sigma of X. So you can write it as P into 1 minus P. Okay, so by that same logic, it will be F into 1 minus F, and then
X1.
then it will be X1. So now you can see that due to this uh, due to this particular sigmoid function, you are getting this particular term, and for this W1 X1, you are getting this term. So your uh, activation function should always be differential. So this is another question. This is not related to this particular question. So let us consider you have a threshold function, threshold activation. So can you use this threshold activation for gradient descent?
No.
Yes, because it is not differentiable. And as it is not differentiable, you will not be able to evaluate the value like this. For example, what you are doing in case of sigmoid function. So as the differentiation is not basically, it is not differentiable. Hence, you cannot use threshold function for gradient descent. Very well. Now, what is the problem that lies with this? But what is the problem that lies with this sigmoid and ReLU? So over here, you can see that the rate of change as you move to higher value of X, if the X value is very high, the rate of change in this particular line is very, very slow. That means almost there is very minor perturbation is there. Same as what is happens over here also. So the value, so the trend is very smooth. So that means if you take derivative is basically tangent. So if you take the derivative, it is almost zero in both the direction, right? So if you increase the value of X, if I write the gradient descent equation Wn plus 1, Wn minus del L by del W. And from the equation of sigmoid, you can see that the value is F into 1 minus F, right? The value is F into 1 minus F into eta into, let's say, X1, Wn n plus 1. Now, if you increase the value of X, so you can see that for this part, the value will reach to 1. So the F value will be 1. So 1 minus 1 will be 0. That means this whole term will vanish. That means gradient vanishes. Same thing happens when the X value is very small. If X value is very small, the sigmoid output will be 0, almost equal to 0. So if it is 0, then you can see the value will be the multiplication will also vanishes, because if F is equal to 0, then this whole thing will also vanish. So that means for sigmoid function, we actually get to arise a problem, which is basically the uh, vanishing gradient. Vanishing gradient problem. So for this part, if you increase the value of X substantially large, and if you decrease the value of X substantially low, for these two regions, you can see the gradient will be vanished. And if the gradient is vanished, then this particular term, whole term will be 0, and your learning will be stopped, as because Wn plus 1 is equals to Wn. That means there is almost no update in gradient descent using gradient descent rule. So your learning process will stop there, and it may so happen that you will be stuck at any of the local minima. So this problem basically called as vanishing gradient problem, where the gradient vanishes due to the saturation of both the parts of sigmoid function. But in case of ReLU, the derivative will be 1, because for here y is equals to x, here y is equals to 0. So over here the derivative will be del x of y will be 0. Over here del x y is equals to 1. So at least for this particular region, for this particular whole region, you can see the derivative exists. And as the derivative exists, so there is no point of vanishing gradient. And here the function itself, as it clips the value to 0. So this part you can omit, but at least you can see for the positive half side. So there is no point of vanishing gradient as the derivative is 1 unity. So this is the advantage of ReLU over sigmoid. The same problem persists in tan h function also. If you look at the diagram of tan h, you will see that it ranges from +1 to -1. And again, you can see that over here saturation is there. Over here also the data is saturated. That means the gradient in all this direction will be very low. If I take gradient, the value will be very low. And as the value is very low, then again you will end up in getting this particular sort of operation, that is the vanishing gradient. So let us scan through the solution, and another thing is that the sigmoid function outputs sigmoid of x for any value of for if we put any value over here, it will give some real output. And over here, the ReLU of x, it will give either 0 or x. And in a matrix, for example, like this, if x1, x2, x3, xn value is passed through ReLU, if any of these x, let us consider majority of the x are negative. So for negative value, the ReLU output will be, most of the value will be 0, 0, 0. Some of the value will be x, x, x. So if in a matrix, most of the values are 0, that matrix or that vector is called sparse. Sparse means where most of the values are 0. So that means as ReLU outputs 0 or x, that means ReLU gives you a sparse representation, as majority of the value will be 0 if your x is negative. So that is why let us scan through the solution. ReLU helps in creating dense representation, which is not true. Why? Because I have already told that majority of the value will be 0 if x is negative. So that means ReLU gives you a sparse representation. So this is incorrect. Next option is ReLU helps in creating sparse. Most of the neuron will be non-active. Non-active means they will output 0 value. So that means this is correct. ReLU helps in mitigating the vanishing gradient, and we have seen that yes, it helps in mitigating vanishing gradient to some extent, at least for the positive half side. So over here, option C is correct. So therefore, option D is the correct option, both B and C. So any confusion for this particular question?
Sir, can you explain option number C?
Yeah. Option C is vanishing. First, we need to understand what is vanishing gradient. So if so let's say you have a function f of w, and which is sigma into w into x, right? Now let us take the gradient with respect to w. So it will be first it will do the derivative with respect to this whole sigmoid function, and we know that the sigmoid function has the derivative as sigma of something, then 1 minus sigma of that argument. And then we have to take the derivative of whatever argument is present inside the sigmoid function. So as because we are taking derivative with respect to w, therefore the derivative of wx will be x only. So that means if I write it like this, it will be f 1 minus f and x del f w del w. Now, if I write the gradient descent equation, it is wn plus 1 is wn minus eta into del f w divided by del w. Right? Now, if I expand this equation, wn plus 1, wn eta, then you have f 1 minus f into x. Now you plot the sigmoid function, which is f of, let's say, f of something. So the sigmoid function looks like this. This is 0.5, this is 1, and this is 0. Now, if you increase, let's say your x value is very high. Let us consider x value is very high. SA for sigmoid. If x value is very high, then you can see wn plus 1, wn minus eta. So let us consider if x is very high, your sigmoid output will be how much? Almost equal to 1. Is it not? When x is very high, what will be the output of this sigmoid function?
1.
1. So let us consider the value is almost equal to 1. So 1 into 1 minus 1 into x. So 1 minus 1, you can see that this will be 0. This whole multiplication will vanish. So this is, so your equation will be wn plus 1 is equals to wn. As the gradient vanishes, this is what gradient vanishing means. That means this whole multiplication term will be equal to 0. As this gradient vanishes, the learning process will stop. As because at n plus 1th iteration, whatever the weight value, that is equal to nth iterations weight value. So this problem is called vanishing gradient. Now let us take case 2. When the value of x is substantially very low, that means x value lies in this particular region. So then what will be the value of sigmoid output? What will be the value of sigmoid output when this x value is very small? What will be the value?
0.
0. So in this particular case, let me write the weight updation equation again. wn plus 1, wn minus eta. So over here, f value is 0. So eta into 0 into 1 minus 0 into x. So again, you can see that this gradient term vanishes. Whole multiplication term is equal to 0. So that means again you are ending up to the same equation, wn plus 1 is equals to wn. So that means the moment the gradient is equals to 0, your learning process will stop. And this problem is called vanishing gradient, as this whole gradient term vanishes due to this saturation part for this part and for this part. That means for sigmoid function, for sigmoid, we can observe vanishing gradient. Okay. Now let us scan through for ReLU. In case of ReLU, the function looks like this. So y is equals to max of 0, x. That means for negative side, it is 0. For positive side, it is x. So again, let's say you have ReLU of w into x. You have a function which is ReLU of w into x. And now you have been told to take the gradient with respect to w. So first thing is what? First thing is gradient of activation function. From this particular equation, we have seen if I take the gradient of this function with respect to w, what basically comes first is the gradient of the activation function. Then we take the gradient of the argument. So over here also we'll get the same thing. Over here what we'll get is gradient of ReLU multiplied with this particular terms gradient del w of w into x. So that is gradient of ReLU multiplied with x. Now let us take two cases. Case 1. Let us consider x is high. So x is high, that means it will range in this particular area. So when x is very high, output is y equal to x. So if I take the derivative of the activation function in this particular region, del y by del x, so the activation function's derivative will be what? 1. So I can write del f by del w is equal to 1 into x. Now let me write the gradient descent equation. Wn plus 1 wn minus eta into del f del w. So I can write it as wn minus eta into 1 into x. Now you can see the gradient does not vanish. But in case of sigmoid, we can see the gradient was vanishing. So this is what basically ReLU helps in. ReLU basically mitigates the gradient descent problem.
Okay, sir. Thank you.
Okay. So option D is correct. So most of the output will be sparse. ReLU helps in mitigating the gradient descent as because at least for this part, you can see that gradient is not vanishing. So this helps in reducing the problem of gradient vanishing. Okay. So next question is, suppose you have a fully connected neural network has a single hidden layer with 50 nodes. So whenever this kind of problem comes, I will suggest is to first visualize the situation. So in a neural network, what are the types of layer that you have? What are the types of layer you can expect in case of a neural network? Anyone? In a neural network, what are the types of layers that you can expect?
Input layer, hidden layer, and output layer.
Yes, so this is your output layer. This is your input layer and this is your hidden layer. So they have said that you have a single hidden layer. So only one hidden layer with 50 nodes. That means you have 50 neurons like this. So 50 cross 1. 50 number of neurons are there. You have a 5-dimensional feature vector as input. The input is 5-dimensional feature vector. That means input has 5 values. That means x1, x2, x3, x4, x5. So it is 5 cross 1. Now you have a binary classification problem. So in case of binary classification problem, what kind of activation function we use?
Sigmoid.
Yes, sigmoid. Sigmoid gives you the value ranging from 0 to 1. And if a binary classification problem is concerned, so our target will be predicting that whether the image belongs to class 0 or it belongs to class 1. So this serves the purpose of binary classification. And in case of multi-class classification, what sort of activation function we use?
Softmax.
Softmax, because softmax, what it does, let's say you have three classes, 1, 2, 3, it gives you a probability distribution like this. What we have seen in week 4 lecture, for example, you have three class problem. Yes, let's say you have three class problem, so you can see that you get a probability distribution. So this is very small because the value is 0.09. This is high because it is 0.67, and another one is little bit higher than this one. This is 0.24. And for whichever class, let's say this is class 1, this is class 2, this is class 3. For whichever class this probability value is maximum, we consider that that particular sample belongs to that class. So over here we can see that for class 1 the probability value is highest. So that means we can say that this image belongs to class 1. So this is how the binary classification and multi-class classification you can do in the regime of neural network architecture. So output has one node because you need to produce an output whether this is 0 or 1, and what basically sigmoid does. So this is the architecture of this whole neural network. Now the question states that uh, calculate the total number of parameters in the network. So the parameter basically in case of a neural network, the parameters are weights and biases. These are the parameters, right? Now in the question they have said that consider there is no bias in this network. So we don't have to think about bias. Generally, weights and bias, they both of the things have to be considered. But as per this question, they have said there is no bias, so we don't have to bother about the bias. So currently the parameter is only the weights. So this is weight for this first layer W1. This is weight for the second layer. So we need to find that how many weights we have to incorporate. So that is basically gives you the total number of parameter. So over here you can see that that your input vector has 5 number of neurons out, and the next layer has 50 number of neurons. To do the matrix multiplication, you have to have weight value is equal to 5 into 50. And why? We know that it is W transpose into X, right? So X is belongs to R 5 cross 1. And let us consider the output of this particular operation is Y. Y is 50 cross 1. So W transpose is uh, uh, so it will be x1, x2, x3 dot x5. So over here it is 5 cross 1, and the W transpose, if you take the W transpose, it will be a matrix of shape. It will be a matrix of shape 50 cross 5. Now you do the matrix multiplication. So 5, 5 will cancel. So you will get 50 cross 1 as the output, which is basically the output of this particular hidden layer. So therefore your weight matrix should have a value 5 cross 50. Similarly, for the second case, the weight 2 will have a shape of 50 cross 1. So again, let us check whether the output value is of 1 cross 1 shape or not. So let us consider the output is y3. So y3 is, and over here, let's say this particular output is x2. So y3 is w2 transpose into x2. So w2 is a matrix of 50 cross 1. So it will be, if I take transpose, it will be 1 cross 50, and x2 has a shape of 50 cross 1. So it will be a tall vector which is having 50 cross 1. So now again, by the law of matrix multiplication, the output will be of shape 1 cross 1. So that means we can understand that all the matrix dimensionalities are okay, as because the final one has to be of shape 1 cross 1, and that is what we are getting from this whole matrix multiplication. So the shape of W1, so the shape of W1 will be 5 cross 50, and shape of W2 will be 50 cross 1. So that means how many number of elements are there in W1? How many elements are there in W1?
250.
250. So parameter of W1 is 250. And similarly, parameter of W2 is how much?
50 parameters.
50 parameters. 50. So total number of parameter will be equal to 300. So this is how you can evaluate the number of parameters in case of a simple. Yes.
So we can do it directly that the number of weight, every neuron is connected to every hidden layer neuron. So how many combination, that is each neuron to 50 layers. So there are 5 to 5 into 50.
Yes, yes, yes. Uh, you can use that particular analogy also, because you are saying that every neuron is connected to the next neuron, and over here you have 5. So how many connection will be there? Such 50 connections. So it will be 5 cross 50. So that is also another way of arguing this particular solution. So that is also correct. You can use that particular analogy as well.
Okay, sir. Thank you.
Okay. Okay, so you have three input neuron has weights. So you have 3 input neuron x1, x2, and x3. W1, W2, W3. They have given the value of weights. The transfer function is linear with a constant of proportionality being equal to 2, and the input values are also given. So so what is basically meant by a transfer function? Anyone?
The activation. The function in frequency domain.
Function in frequency domain is okay, but let us consider you have a system H which has an input X and it gives you an output Y. So H basically, let's say, as because you told that frequency domain, let me consider the frequency domain as the Laplace domain. So Hs is the transfer function. It is Ys divided by Xs, considering all initial conditions equal to 0. I'm not going into the details of the signal system because there are other conditions also, because let us you have to consider that this is an LTI system. So for LTI system, this condition holds. But let us just take some inference from this representation. So this is what is called as transfer function. And you can see transfer function is basically the crude way of explaining is transfer function could be output divided by input. So from here we can see that the if this is the neuron gives you the output Y, and it takes the linear combination of these inputs. That means W1 x1, W2 x2, W3 x3. So transfer function is y divided by wi xi from this particular analogy. This is the output. So this is the output and this is the input. Now input is what? Input is basically the linear combination of these inputs, that is W1 x1, W2 x2 and W3 x3. So that is what we have written. And they have said that with a proportionality constant being 2. So that means if you take the ratio of these two, you will get a proportionality constant 2. Or in a lighter way, it is basically explained as y is proportional to wyxi, and you can say that this is the proportionality constant k wyxi, and the value of k is 2 wyxi. So this could be another way of illustration. So this is first illustration and this is the second illustration. Okay.
Yes.
So now we just have to calculate what is the value of y. So it will be
So 40.
w1 x1. What will be the value of x? What will be the final value again?
So 40 answer is coming 40.
Answer is coming 40. Let me just check. So this is 1.5, 20 into sorry, 1.5 multiplied 6, 20 into 0.5 and 4 into 0.5. So it is 2 multiplied with, this will be 9, this will be 10, and this will be 20. So 2. So 2 into 21. Can you check your calculation again? So it is coming, I think 42. I don't know whether I have made any mistake
Yes,
in the
sir. I
calculation.
miscalculated. I miscalculated.
So it is 42, right?
Yes, sir.
Yes, sir.
Okay. So the answer is 42. And we have already discussed about this particular question also in the previous slide. So let me just read it out. You want to build a 5-class neural network classifier. That means 5-class neural network classifier means whether it's a binary classification or multi-class classification.
Multi-class.
Multi-class classification. So given a leaf image, you want to classify which of the 5 leaf breed it belongs to. Which of the among 4 options will be appropriate to use as a loss function? So for multi-class classification, what is the loss function that we use? In case of binary classification, we use binary cross entropy. And in case of multi-class classification, what we use? We use multi-class categorical cross entropy. So it is there in probably loss functions lecture. So categorical cross entropy loss function. So Professor PKV has shown you 2 sets of loss function. One is the binary cross entropy, which is basically given as y into log of O plus 1 minus y into log of 1 minus O. So this is basically the binary cross entropy, and the same thing will persist. And you have to take the average value for let's say you have n number of classes, so you have to do this whole thing for n times, and you take the average. So this is basically called the multi-class categorical cross entropy. So over here we have MSE loss. So MSE is not used. SSIM is called structural similarity index. So SSIM is also not used. You will see in probably 12th week or something, when semantic segmentation will come. So people uses this particular loss function for those applications. So as we have not covered the semantic segmentation and all, I'm not explaining the SSIM loss. But as far as MSE loss is concerned, we do not use MSE for classification task. So the final option is cross entropy loss. So for 5-class classification, we use cross entropy. So the option could be more precise. They could have write multi-class categorical cross entropy, because there are two sets of cross entropy loss. One is the binary cross entropy and one is the multi-class categorical cross entropy loss function. So the final answer will be option A. So this thorough description you will find in the lecture loss function. You can refer to that lecture, loss function.
Sir, MSc loss functions are used where?
They are used in regression application. Let me tell you what is then regression. So let's say you have a neural network. You are giving value x1, x2, dot x5. And in case of let's say binary classification, your output will be either 0 or 1. That means either it belongs to class 0 or it belongs to class 1. That means you have to output two discrete values. So this problem is called classification. In case of regression, you have x1, x2, dot xn, and you have a input layer, hidden layer. Subsequent to that, you have an output layer. And given this x1, x2, xn, let's say you want to generate some real numbers. Let's say y1, y2, y3, y5. So that means given real values, you need to generate real values itself. This problem is called regression problem. If I give you one example, it could be, for example, the stock market data analysis. So let's say given 5 days stock market data, you need to predict that what would be the observation for 6th day. That means you need to generate some real numbers for this. So this problem is called regression problem. That means you have been given 5 days data. You need to predict what will be the data for 6th day. That means you need to generate some sort of real numbers. So those problems are called regression. So for those operations, you have to use the MSE loss function.
Okay, sir. Got it.
Okay, so with this, we have covered the week 5 practice problem as well as week 4 quiz questions as well. So as we planned, let me just quickly show you the SVM and KNN implementation. So these parts you have already been familiar with. So first is to do the simulation. First, you need to import different sorts of libraries. For example, NumPy is for any sort of NumPy array operations. Then the counter is basically to count the numbers. Then sklearn is basically known as scikit-learn. So in case of scikit-learn, we use it for different machine learning applications and statistical analysis of application. So for example, we can use it for doing the implementation of SVM, KNN, and all this machine learning application. Then we have imported TensorFlow as well to actually refer to some of the standard machine learning, deep learning data sets. So we are focusing our implementation for the Cipher10 dataset as well as MNIST dataset. So MNIST dataset comprises the handwritten digits recognition problem, and Cipher10 dataset basically comprises a 10 class classification problem, which comprises the images such as frog, bird, truck, horse, etc., automobile, aeroplane, something like that. So what I am doing over here is I am actually importing the data set, and I am showing that what sort of images it basically has, the Cipher10 data set. So this is the loading of Cipher10, and I'm visualizing it as well, that how Cipher10 data set looks like. So here I'm showing first 100 images. So what are the first 100 images are there, and as well as I'm writing their label as well. So you can see this is a horse, this is a truck, horse, frog, so like that. So these all images are, these kind of images are there. And the shape of these images, how you will get the shape of these images. So let me just show you the shape. XP dot shape. So you have this 50,000 means you have 50,000 such images, and each of the images are of shape 32 by 32 by 3. Why 3? Because these are color images. So in case of color images, there will be 3 plane: red, green, and blue. RGB planes will be there. So as because 3 planes are there, so you have three three channels in those particular images, and each of the channels are of size 32 by 32. And as because these are 32 by 32, you can see that image resolution is very poor. So these are very low resolution images. So that is why they are kind of blurry. Okay. So in the lecture, you have seen that if you have an image, so
Sir, I
yes,
wish to ask something.
yes.
Sir, I want to confirm that if it's a classification problem, it's a clear distinction between the two of the classes and assigning the value 0 or 1. And if it's a regression problem, it's not a clear distinction of the values. It's just assigning some probable values to which of the things is probable.
Yeah, like
Okay,
that.
okay.
For example, uh, let's say you have training data. So for training data, you know what is the response. That means, let's say this is your first 5 days data, and this is the original 6th day data. Okay, so this is 6th day. So this is what you know, and what your machine learning will do. You will show that machine learning this 5-day data. Now the machine learning model has to predict this 6th day data. So let us consider it predicts it like this, a straight line. So this is model prediction. Sorry, this is model output, and this is the true or target. So your model has to predict something like that, like this, but it is predicting the straight line. So how you can reduce the loss? Now you have the real numbers. So these are real numbers. These are also real numbers. So you can take MSE like y hat minus y square divided by for all I. So for each and every point, you take the difference, then square it, then take the average. So this is what MSE loss is. So that means for regression problem, you need to use MSE, as because you need to predict the real values. Got it?
Yes, sir, got it.
Okay. Okay, so this is the visualization of the data set. Followed by that, now what I'm doing is basically loading the training data as well as the testing data. And we have seen in the lecture that if you have an image, let's say a 28 by 28 image, How you can generate features? You can take one column, place it like this, second column, just append it like this, then do the same, the last column, you
So
place it
28
like
feature
this.
vectors of 1 cross 28.
Yeah, 28 feature vectors of 1 plus 28. So it will result you to 784 cross 1. So such 28 feature vectors are there. So in total it will look like this, which will have a shape of 784 cross 1. So by that same logic, I'm trying to produce the same operation. So I'm trying to reshape it. So reshape X train comma shape 0. That means it will give you that 50,000 images. And if you put -1, then what it will do, it will flatten the whole image. So if I just run it, you will see that what is the shape. So now you can see you are getting 3072. Now how this 3072 is coming? You have 32 by 32 by 3. So if you just flatten the image, so 32 by 32 by 3, if you just do this operation, so it will give you 3072 value. That means you are flattening the whole image, doing the same operation that I have shown over here. So this is for one particular channel. If you have RGB image, so for the red channel, you do the same. That means again, it will be like this. Then if you have green channel, again, you need to append beneath this one. So you will have data looking like this, then followed by the red channel data, and then followed by the green channel data. So it will be 32 by 32 by 3. So if you do the multiplication, it will be 3072. So that means this data will have shape 3072 cross 1. Now in the training data set, you have 50,000 such images. So for the whole data set, the shape will be 50,000 such images multiplied with 3072. Or you can consider 3072 cross 1. This is for a single image. For 50,000 images, this is the whole thing. So that is what you can see over here. So for 50,000 images, you are having this 3072 number of data. Fine. Now you can define KNN classifier by your own. You can write it from scratch, or what you can do, you can use the predefined method. For example, you have the sklearn library. You can import from sklearn library. For example, over here I have imported. So from sklearn dot neighbors, import k near neighbor classifier. So if you just import this thing, you don't have to write the KNN classifier by your own. So over here I have written a KNN classifier by my own so that you can skim through. So the basic idea is that KNN implementation. So these are the steps that you have to actually follow. So in case of KNN, let us consider we have two features, x1 and x2. So what you will do, first you will project all these x1 and x2 in the feature plane. So like this, let us consider x1, the 2-class problem we have. So this looks like this. Now you put an unknown feature vector over here. Then you calculate the distance from all these points. From all these points, you calculate the distance. Then you consider a neighborhood, let's say neighbor equal to 3. Then you search for this neighborhood. Then you can search for this neighborhood. And you will see that for which of the classes is coming maximum. Then you can consider that X belongs to this red class. So over here, you can see that for the red class, the distance values are minimum. So that means X will be classified as it belongs to red class. So let me show you through this particular KNN application. So we have considered the Euclidean distance. That means root over x1 square minus x2 square. So class is KNN. So you can define it as k equal to 3. K equal to 3 means the neighbor value that I'm considering is 3. 3 neighbors I'm considering. Then what you have to do is basically fit the training input. So I am defining fit as self function. Self function will basically gives you a container on top of which you can actually store the xtrain and ytrain. So it basically acts as an object to this xtrain and ytrain. So over here self dot xtrain is equals to xtrain and self dot ytrain is equals to ytrain. It basically indicates that what is the value of xtrain and what is the value of ytrain. Then after you place all these training samples, you provide a test sample. So that is what we are doing, and you need to predict that at which class basically x test belongs to. So it will be done through this predict function. So predict self comma x test. So you have, let's say, 50,000 such images. So for 50, you have in the test set, you have 10,000 images. So for all these 10,000 images, you will have some predictions. So all these predictions will be stored in a list. So that is why I have created a list. So this is a data structure. This is a data structure. So this data structure is called list in Python. So let me just uh, give a comment. So list type data, and the total number of samples in the test set will be length of x test. That means this will be 10,000 actually. So for each of these 10,000 test samples. So for each of the test samples, you will do the prediction, and whatever prediction comes out, that will be stored in prediction list. Now you write a for loop for all these 10,000 images. You will write a for loop. So for I comma x in enumerate x test means it will give you the total number of such images or total number of such vectors that basically comprises in x test. Then you have to calculate the distance for a given test query. You have to calculate all possible distance values for the which are there in the training set. So that is what we are calculating. Distance is equal to Euclidean distance between x and x train. That means if I just show it over here, so that means you have a test query and these are two classes. So you need to calculate the distance between all these points. Similarly for this one and this one as well. So that is what we are doing over here. Euclidean distance x comma x train for x train in self x train. That means I am inferring to all this data that I have provided over here. Then you need to sort. So again, let me just refer to this. So after you calculate all these distance, let's say D1, D2, till let's say I have total 100 data points in the training data set. So 100 distance you have calculated. Now what you will do, you will arrange all these distance values in this particular order from lower to higher. So let's say the distances are D1, D2, dot, 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 D100. Now you have to arrange them, actually sort them from lower to higher order. So by that logic, let's say if D50 comes over here, let's say D50 is the lowest value, then D40 like that, let's say D10. If it is like this, then you have to consider first k number of observations, and then you have to see that for which of the classes the value is very less, and then you can predict it. And that is what we are doing over here. So K indices, it basically gives you the indices for which the values have to be sorted. Then extract the label of K nearest neighbor from the training sample. So now you have got the sorted distance values. Now D50, let's say this gives you D50. So this D50 you will get a label from the label set is that, okay, this belongs to blue class. Let's say D40 is this one. So this D40, you will see this is red class. Let's say the next one, let's say D50, D40, D30, and this is what D30 is. So you have considered a k value of 3, k equal to 3. So D, this one belongs to blue class, this one belongs to red class, and this one belongs to blue class. So you can see that if I take the most of the relevant outcomes, you take mode of all these things. So which of this is frequently coming? Blue is frequently coming, as because the number of blue is higher. So that means you can consider that using k equal to 3, your classification your classification output is that this pink data point belongs to blue class. So that is what we are doing in the code itself, that you are extracting the labels for the for those sort of distance values, and then you're trying to extract that which of the label is coming as a most common. So that is what we are doing. So which of the label is coming as most common? So over here, blue is coming as most common. So that is why we are classifying it as the data belongs to blue class. So over here, you have taken the counter operation. So you count it that which of the class is coming more frequently, and then you consider this most common as the prediction. And after doing all these things, let's say uh, this basically takes time to train. So I have written a print progress that after each and every 100 equation, it will show that how many distance have been calculated. So let me just train the KNN classifier with my own KNN. It is not from the scikit-learn library. I have written it from scratch. So I have considered k value equal to 5. So in last to last class, one person was asking that what k value should we consider? So you can actually, this k value is a hyperparameter. You can check with different values of k, and for whichever k value the accuracy is coming maximum, you can consider that you have to consider for that particular k value. So this is a hyperparameter. You just have to plug and play with different values, and you need to check for which of the values you are getting the highest classification accuracy. So it takes some time, probably 2 to 3 minutes to train the whole KNN model. So let us just wait till then. Yeah, meanwhile, if you have any confusion, you can just ask. So now you can see out of 400 samples, 100 sample has been completed. 100 distance have been processed. So now you can see that in the test set, actually, you have 10,000 images actually. Over here, you can see in the test set, you have 10,000 images, but I have considered only 400 images. You can see that how much time it takes to train the model. So that is why actually, if the system hardware is good enough, then it will take lesser time. So for 400 images, it will take probably around 4 to 5 minutes. And you can understand that for 10,000 images, how much time it will take to train the whole KNN model. So you can just omit this thing, just put when you will run it by yourself. So you can just comment it. So it will not consider the 400 images. It will consider whole 10,000 images, and then you can train for whole 10,000 images. But as because it will take substantially huge amount of time, so therefore I have just restricted myself to restrict myself for 400 images only. So till now 300. Yes, please go ahead.
Sir, how it will select 400 image randomly
Yeah,
or
yeah, first 400, first 400.
first four? Okay, sir. Okay.
Yeah, first
Okay, thank
400. Yeah, so 400 images have been processed, and you can see that accuracy is 0.335. That means 33.5% accuracy you are getting. But it may so happen that if you increase the number of images, so it will be able to learn more. So if you show more number of instances, your model gets quite acquainted with the classification problem. So it will better solve the problem. As because I have just restricted myself for 400 images, so that is what you can see, that the accuracy is quite less, 33.5% only. So you can use all 10,000 images and you can see that what is the performance. And you can change the value of K as well. So it will show that for which of the K values is suitable for this particular application. And again, let me tell you, for each problem, for problem to problem, the value of K will vary, because nobody knows that for which value of K your algorithm will work with for a particular data set. For example, in case of cipher 10 data set, K value equal to 3 will give you highest accuracy. But for MNIST data set, K value equal to 7 or K value equal to 6 may give you highest accuracy. So you should not infer to such conclusion that K value equal to 5 or K value equal to 3 will only give you the highest accuracy. This is a hyperparameter. You need to tune these hyperparameters. Okay, so this is what we got from a KNN written from scratch. So let us just verify with the standard KNN library. So nobody uses this sort of KNN class because you have standard libraries, and standard libraries are pretty much efficient in calculating all these matrix operations. So let me just do the same thing, and then let us check for the whole data set. Now, what is the classification accuracy? So now you can see I have considered all 10,000 images, all 10,000 images. Now let us check that within how much time we are getting the final output. So for 400 images, if I have written a KNN from scratch, it takes 4 minutes to give me the classification accuracy only for 400 images. But let us consider the standard library that is there in case of sklearn, and we'll be using all 10,000 images, and we'll see that what will be the classification accuracy and as well as how much time it takes. So you can see for all 10,000 images, still the accuracy is 33% only. And it takes only 1 minute. This is the main point, that it takes only 1 minute to process all such 10,000 images. And this is why you should rely upon these standard library based commands, because here the operation that I have written just a simple iterative approach. That means for each iteration, it will take a value, it will take distance from this particular value, it will take distance from this particular to this particular point. So it takes huge amount of time to do this. But if you see the original documentation of K nearest neighborhood, you will see that they have used different sorts of data structure to implement this K nearest neighbor classifier, and which basically ensures the computation will be very fast and the computational complexity will be substantially low. So that is why you should rely, you should use these uh, predefined libraries for using it in the any deep learning machine learning application. It is always preferred that you can write, if you are able to write your own algorithm, that is fine. But if that is a standard classifier, then I would recommend you to use the libraries rather than writing them by your own. Okay, so let us do the same for MNIST dataset. So over here, I am loading the MNIST dataset, then I am flattening the images, and then I'm using a KNN, so K nearest neighborhood. And in case of MNIST dataset, I have deliberately put K value, that means N near neighbor value equal to 4. And let us check that whether we are getting a good classification accuracy or not. So you can see that let us first check that how many test images are there in case of MNIST dataset. So xtest.shape is 10,000. That means you have 10,000 images again, which has shape of 784. Now you can see that within 31 seconds your computation is done. And with K value or nearest neighbor value equal to 4, you are getting accuracy 96%. So this again proves that this nearest value is a hyperparameter. So you have to use different sort of hyperparameter, different sort of K values, and then you can check that which K value yields the highest accuracy. Here I have used 4. You can check with 3, 2, then 5, 7, whatever value, and then you can see that for which of the K values you are getting the highest accuracy. So that particular K value you need to consider. Okay, so with this, KNN is covered, and let us move to support vector machine. So again, as I have shown you that uh, for doing the machine learning, deep learning applications, you should rely upon the what you call the standard libraries. So like the KNN, in case of SVM also, you have sklearn library support. So from sklearn .svm import linear SVC. So this basically gives you the linear machine that you have learned in week 4. So linear machine is basically inferred from this particular command. So in linear SVM, Professor PK Viswas has shown that if you uh, extract the weights, and if you unravel the weights, you will see the template of the data. So that is what we will try to do. And we will use MNIST dataset to do that. So over here, what I'm doing is I'm loading the MNIST dataset. Then I'm flattening the images that we have already seen. Then I'm normalizing it to make the values in the range of 0 to 1. In the range of 0 to 1. And then I have written SVM equal to linear SVC. This is just to this is just to create an SVM operator. And then what I will do is svm.fit. So whenever you write fit, that means you are creating a SVM using by employing the training data. So in the training data, you have features as well as the labels. Now this will ensure the training of the SVM. Now, after you train the SVM in the SVM optimization function, you have seen that our aim is to, if margin is 2 by mod W, we need to increase the margin. That means with respect to what? With respect to these weight values. So that means we need to optimize this margin with respect to W values. So that means we are learning the weight values. So over here, what I am doing after training the whole model, I am extracting the learned weight values so that I am storing in coef. That means coefficient. So if you write svm.coef, it will give you the weight values. So uh, let me first remove this part or just show you the. Yes, let me first train the SVM. So loading the MNIS, flattening the images, normalizing, and then svm.fit will train a SVM. So in the training set, you have 50,000 images. So let us check within how much time this training process completes. It probably takes 2 to 3 minutes to train the whole model using the standard library. I trained it with my own SVM also. So it took around uh, 20 to 25 minutes. So you can see that within 1 minute 41 seconds, this whole training has been completed. OK, so after you train the SVM, let us check the classification accuracy. What you will do, you will feed the test images into the trained SVM. So for predicting, you will write SVM dot predict. And on top of what? On top of the test images. So it will give you Y predictions, and then you can extract the accuracy using accuracy score method. That is also there in sklearn library. So you can see that accuracy is 91.81%. So it is in terms of the point value, but if you just multiply it with 100, it will give you 98.18%, 81% accuracy. OK, so can anyone tell me that what will be the value of what will be the shape of the weight matrix? What will be the shape of the weight matrix? Yes, anyone? Okay, in case of a linear SVM, you have seen that there is a weight matrix W, and you multiply with some feature. So if you have, let's say, k number of classes, k number of classes, and for each class you have d number of features. So in our case, we have 784 number of features and we have 10 classes because the data set comprises 0, 1, 2, dot, dot, 9. So we have total 10 classes. So this is a 10 class classification problem. And for each of the images, we have 784 features. So the weight matrix will have shape 10 cross 784. Or the transpose is also valid. So we can see that this is the coefficient shape, that is 10 cross 784. So 10 basically refers to the number of number of classes, and 784 basically refers to the number of features. Okay. And then if I show you the yes.
The number of classes, how many different types of picture images we are given, like that it will calculate, or how it will calculate?
Okay, so let me show you the by what is the name? Y test. So for each and every image, you have label. For example, if the image is, let's say, image is like this, so they have given, so this is X, and they have written the label as 0. If a image is 1, then the label is 1. So if I just see that what are the labels present, so it will give me 0, 1, 2, dot, 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 9. So from there we'll be able to know that how many classes are there. So np.unique. So you can see that these are the labels 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that means total 10 types of images we have. Total 10 types of images we have in the data set. So yes, please go ahead.
Thank you.
Okay, so with this, that is why this 10 is coming, because we have the images of 0, 1, 2 till 9. So total 10 classes. And for each of the classes, we have 784 dimensional feature vector. Now, let me just show you for each of the class how the template looks like. So over here, you can see that for each of the class, how the template looks like. So in Cypher 10 dataset, in the lecture, you would have seen that you can clearly distinct that for bird class you will see the template of bird. In case of frog class you will see the template of frog, but in case of MNIST dataset you are not able to capture very high definition, or you cannot capture the class dependent templates, but you have some representations. So you can do the same for Cypher 10 dataset. So I have written the code, and you can just train the Cypher 10 SVM on Cypher 10 dataset, and you can just do the unraveling of the weight coefficient, and you will see that for bird class you will see a template of bird, for a frog class of a template of frog, like that, which is there in the course in the week 3 lecture. So those images you can generate by yourself also by using this code. But the main problem is, if your system doesn't have very good hardware, then it will take ages to train a SVM model. So in my case, it took around 3.5 hours to train the whole model. So that is why I am not running the model now, because it will take 3 hours, and nobody will sit for 3 hours to see that training progress is going on. So you can do it by yourself. If your system has good hardware, then you can train it. Otherwise, this is just to show you that how for each and every class the template looks like. So using this particular code, you can replicate the same for Cypher 10 database. And that is why I have comment it out, train at your own risk, because it will take minimum 4 or 5 hours at a normal machine. Okay, so with this, we have actually completed the implementation part for SVM and KNN. So I have already shared this in my GitHub profile. So you can go to GitHub profile and you can just press this open in Colab. So it will head you to Colab directly. So you don't have to download and upload it in Google Colab. So there is a button given. This button is given in GitHub. So you can just click on this and it will move you to Colab, and directly you can start doing the coding by your own. So I have shared it already. It is there in the GitHub profile. So if you have any further queries, then I can take. Otherwise, we can end the session here. Yes, any query?
Okay. Your beta profile means in Google we have to type in CSA.
Sorry. GitHub profile.
Yeah.
Yeah, GitHub
Where
profile.
it is provided.
I'll show you that where it is provided. So you go to the course website. See, you go to the course website. Then let me just sign in. And I would also request you to fill the Google form for problem solving sessions that is given here. So please submit this survey also. So you go to the problem solving session. Let me just zoom it a bit. You go to the problem solving recording, click it. Then it will get you to the log sheet. So in the log sheet, so this is my part and this is the other TA. So over here you can see that the GitHub link is provided. So you just click on the GitHub link. So it will head you to my GitHub account.
Okay, sir. Thank you.
Okay. So here in week 3, I have uploaded the code, so you can check it from here. So you go to week 3. And then the button will come and then it will head you to the Google Colab platform. Okay, any other query?
Okay, sir.
Okay.
Thank you very
Okay, so we can stop the lecture here.
Okay, sir. Thank you so much.
Thank you, sir. Yeah, thank you. Yeah. Yeah, okay, so I'm ending the meeting.